Good afternoon, everybody. Today we're going to do a calculus problem we're going to namely find the volume of an object using the cross sections of that object. Let's see what we have. Okay, the particular solid we're going to look at today is, the solid that lies between the planes that are perpendicular to the x-axis at x equals 0 and x equals 4. So they're going to come out. We're going to have YZ planes, and as it turns out, or YZ not planes, excuse me, cross sections. And these cross sections are going to be squares, as it turns out. That's what we're going to use by choice. And we don't have to use squares. We're choosing to use them. So we want the solid that lies between the planes perpendicular to the x-axis at 0 and 4. The cross sections perpendicular to the axis on the interval from 0 to 4, like I said, are going to be squares, and they're going to be squares whose diagonals run from the parabola y equals negative square root of x. That's a negative sign right there. Let me make that more clear. Negative square root of x to the parabola y equals positive square root of x. So what is happening here is that our squares are tilted such that the diagonals that do run from y equals negative radical x to y equals radical x lie on the board, while two of the edges come out of the board and two of the edges sort of go into the wall. Go into the wall. What's happening is, let me use my finger. The diagonal is on the board. The diagonal of the square is running from here to here. For any cross-section square, the diagonal is going straight down on the y-axis from here to here. So the diagonal is along the y-axis. And then we have YZ, the YZ legs. Now the edges, the edges, I shouldn't say legs, I should say edges. The edges of the squares come out to our faces like this until we get on a parallel to the x-axis. Then we take another 90 degree and we zoom down, and then we go into the board, into the wall, and we kink up. And then imagine my finger is into the wall, and then we turn back around and kink up, and then we're back up here again. So the square is turned over. It's turned so that one of the diagonals is dead straight along the y-axis, and the edges kink like this, then into the wall, and then back up to this point right here. So these are squares along that are in YZ planes. They're perpendicular to the x-axis. That's the hardest part to understand, is how the squares are oriented. I didn't draw the 3D region. I wish I could have, but I just can't draw that well. What it is we would have squares coming out toward our faces and into the board. We'd have a really small square. As we get really close to the origin, we just have a point at the origin. Really small squares, and then progressively bigger squares the edges are 45ers coming out to our faces, going back toward the board, then into the board, then back up to the top point. So these are the cross sections. I wish I could have found the visual for that. I just can't draw it. So these are the squares that we're dealing with. Now, it stands to reason. Now, the diagonal goes from radical x here to negative radical x down here. So that's a length of 2 radical x. Okay, so if we did a little mini sketch, excuse me here. If this right here was the square, notice the diagonal lies on the board. If this is the y and this is the z, I've rescaled them. If we could look at this, imagine we're looking from a different angle. Here's y, here's a y strip, here's a z strip, here's 2 radical x. By Pythagorean theorem and isosceles triangles, this is radical 2x with the 2 inside. And that's, again, by the Pythagorean theorem. The edges themselves have a length of radical 2x with the 2 on the inside. So that we've got squares that are for each x that we choose, the squares have edges that are of length radical 2x with the 2 inside. So finally, now by the definition of volume, we integrate over the area of each particular square, but the area is going to be edge length squared, so we integrate over the squares of the edge lengths. Now that's just going to, so we get 0 to 4 was our boundaries they were our boundaries that we were given. So the 0 to 4 integral, now the square of the square root is just the guy himself, 2x dx. And then by cal 1, that's x squared with the upper and lower limit. And that's equal to 16 by arithmetic. So that the volume of our particular object is 16. And that's what we were looking for there. That's the final answer. It would have been more satisfying. Drawing the 3D region is not easy, but the best way I could tell you to visualize it would be to imagine a bunch of little 45-degree turn squares here, and then here, and then here. And if I tried to draw it, it would probably be a futile effort. My abilities to draw, I may break down and try it here, but my abilities to draw are somewhat lacking. So we've already solved the problem. Just everything inside me, I want to give you the region though. It would just be so much more satisfying if I could do that. Like if we go along the x-axis, we'd have another parabola. And then if I could, and they would be connected by squares. And that's a pretty vain attempt to draw. I'm sorry I couldn't find the region, so we'll just abort mission on that. But it would look something like this. You would have two paraboloids, one above and one below. Really, above and below may not be, like we got this XY parabola here, and then we're wanting the squares that lie along the diagonal. So we would have a bunch of squares that would progress in a parabolic manner. We would have sharp edges here, and we'd keep going further. As we kept going forever this way, we'd have further, our squares would be bigger and bigger. So we'd, it's kind of gradual though after a while. Let me draw. So if I come up here, for example, I do this. I come up, so 45-degree slant, come this way, and then down here, and then into the board, and then back up here again. And that's the best I can do. But this is how these things go, and the squares are 45-degree tilted, and I hope this helps. The most important part was using this cross-sectional area here. And this YZ, these were just to motivate that this was the y-axis and this was the z. But the point is, since the diagonals are 2 radical x, by isosceles, by the theorems of isosceles triangles and by the Pythagoras, this is the square root of 2x. Thank you guys. I hope this helps, and I'll try to do more videos soon. And maybe if I find that visual, I'll do it on another video. I didn't find it this time. Thank you though. Bye-bye.